Empirical risk minimization learning rule is a basic concept of machine learning. So we usually define a loss function and try to minimize the loss in most of our machine learning process. Okay. In this course, let's first consider empirical risk minimization learning rule with very simple scenario. Okay. So what is empirical risk minimization learning rule? Empirical risk minimization learning rule: find HS hypothesis among your hypothesis class that minimize the training error. Okay, the empirical risk computed from your training data point. Okay, so to make your life easier, let's first consider the case there exists H star. So basically, true hypothesis belong to your hypothesis class. Let's first assume that the true hypothesis belong to your hypothesis class. So, which means the true test error, the risk with respect to the true distribution D is equal to 0. Okay, let's assume this. Then, basically, since the sample S comes from the distribution D as well, your H star empirical risk also equal to 0 with probability 1, because the expectation loss, test loss is equal to 0. When you can find H star, then basically the sample error, the empirical risk error, also equal to 0. And since the empirical risk minimization learning rule find the hypothesis that minimize the sample loss, the training error, and we know that there exists H star, the ground truth H, hypothesis H in your hypothesis class, we can say that at least there exists one hypothesis, at least one hypothesis in your hypothesis class that make your training error equal to 0. Okay, so therefore under the assumption, at least we can say that your empirical learning output HS, the learning output HS, satisfy the sample error equal to 0. Right. But this is very important. Although H star belong to your hypothesis class that make a test error equal to 0, and H star also make the sample error, the training error equal to 0, but ELM learning rule cannot guarantee the test error of HS also equal to 0. We cannot guarantee this. Why? Why? Because there are multiple different hypotheses in your hypothesis set that make the sample error equal to 0, the empirical error equal to 0. Which means there could be many different hypotheses that make your sample error equal to 0. So we have to randomly choose one of them for the learning process, because we essentially don't know which hypothesis is true H star among them. Our only information is all these hypotheses make the training error equal to 0, the sample error equal to 0. Except that we don't know, we cannot discriminate H star from the hypothesis making 0 training error. Right? When there are multiple different hypotheses having 0 training error, we cannot guarantee H star is selected as HS. So we cannot guarantee the test error of your HS, the training output, is equal to 0, although H star belong to your hypothesis set. Okay, right. This is very important, and this week we will discuss how many data points do we require to guarantee very nice test error from your empirical risk minimization rule. To this aim, we need first define our learning model more precisely. Okay, this week we need IID assumption as well. What is IID assumption? Basically, the training data randomly sampled from the data generation distribution D independently and identically. So every xi is independently sampled according to the distribution D, and each corresponding label comes from the true function f. Okay, therefore LSH is a random variable. Even you fix a hypothesis H, because as the training set is random set, because we randomly sample every single data point, ls, the empirical risk value of a given hypothesis, is a random variable. Since every LSH is a random variable, HS is also a random variable. Depending on which training data point we have, HS can differ, right? So LD, the test error, actually this is LDF, the test error of your empirical risk minimizer, HS, is also a random variable. So from this, indeed the generalization error, LDF minus LDF HS minus LSHS, usually this is equal to 0 when F belongs to hypothesis class H, or H star make LDF H star equal to 0. So to say about the quality of test error of your empirical risk minimizer, because this is a random variable, we need some probabilistic statement, right? So this is PAC learning. PAC learning is a probabilistic statement on your learning process. Probably, approximately correct learning is called PAC learning. So what is the formal definition of PAC learning? This is the formal definition. Let H be a hypothesis class, and H is PAC learnable if the following property holds. For every epsilon delta in between 0 and 1, and for every distribution D and labeling function f with the realizable assumption. So here the realizable assumption means, where is it? This one. There exists H star in your hypothesis class that make test error 0. Then there exists some sampling rule bound such that when your sampling number, the number of samples for your training is bigger than or equal to this sampling rule bound, the sampling rule bound depend on the epsilon and delta constant here. IID examples generated by this distribution D and labeled by F, the algorithm return H, the empirical risk minimizer H, satisfying the test error is less than or equal to epsilon with probability 1 minus delta. So the key bottom line is this: the algorithm return H satisfying test error less than or equal to epsilon with probability 1 minus delta. So we define the learnability using this probabilistic statement. We define the quality, the epsilon amount of looseness, so epsilon amount of loss on your test error, with probability 1 minus delta. So when you set delta very close to 0 and epsilon also very close to 0, we can guarantee a good performance with high probability, right? But of course, as you decrease epsilon and delta, the sampling low bound NH epsilon delta may be increased. So the key statement is this, and the important part of PAC runnability is what is this sample complexity? How many training data points do we need to guarantee such epsilon delta PAC runnability? That is the main part of our course.